Let's look at this particular question with respect to autocorrelation of a time series. Consider this time series model 1 minus alpha b whole cube xt equal to et, where b is the backward shift operator, et is the white noise with the variance sigma squared, mean will be 0. Determine for which values of alpha the process is stationary. For the process to be stationary, I'll first find out the characteristic polynomial, right? And the roots of that characteristic polynomial, all of them should be, their absolute value should be greater than 1. So for this particular expression, okay, 1 minus alpha some y whole cube is the, because b is the, if I write it in the form of backward shift operator, so once I remove it and replace it with some variable, because I have x, I am using some y. So 1 minus alpha y whole cube is what is my characteristic polynomial. So equating it to 0, I want to, if this process has to be stationary, the roots of this polynomial, what are the roots of this? 1 by alpha is the root. Now this absolute value of the root should be greater than 1, which means here my alpha, or the absolute value of alpha, should be less than 1. In that case, this particular process is a stationary process. Alright. Now, based on that, we are saying take alpha equal to 0.4, which means it's a stationary process. Now, for that, I am asked to write out the Yule-Walker equation. What are the Yule-Walker equation? Basically, you expand this 1 minus of, or probably if you are looking at it, 1 minus of 3 alpha b squared plus 3 alpha squared b minus alpha cube b cube. Okay, here it is minus 3 alpha b plus 3 alpha squared b squared minus alpha cube b cube times xt equal to et. Now I can expand this saying, okay, xt minus 3 alpha, one backward operator for xt, one period lag, which is t minus 1, plus 3 alpha squared b squared xt, two periods lag, xt minus 2, minus alpha cube xt minus 3 is equal to et. So this is the one. Now when we are, this is the typical expression. Now probably I have even alpha equal to 0.4. So probably my expression is going to come out as xt minus 1.2 xt minus 1 plus 3 into 0.4 squared, 0.16, 0.16 into 3, 0.48 xt minus 2 minus, again alpha is, uh, 0.064, right, because 0.4 cube, 0.064 xt minus 3 minus et equal to 0, right? So this is the typical expression, or probably I'm going ahead, so this becomes the equation. Now I really need to take, right, if at all I want to write the Euler-Walker function, it's as good as talking of, I write to find covariance between xt, covariance between xt and xt minus 1. So here probably first thing is I'll write xt here in the form of 1.2 xt minus 1 minus 0.48 xt minus 2 plus 0.064 xt minus 3 plus et. Now we'll take the covariance with respect to each of the time lags. Covariance between xt and xt minus 2. and covariance of xt comma xt minus 3. So these will come out to be our expression. So when I am doing the covariance with respect to xt, for this expression, covariance with respect to xt, okay, this comes out to x. So the covariance with respect to xt is what I am calling as. So here I can very well substitute zeros. Right now, let me do it with respect to 0. Right now that I know this, so probably if I do it with respect to xt, this becomes gamma 0. Right, with respect to xt, if I am doing for this, it becomes gamma xt comma xt, which is gamma 0, is equal to 1.2 times xt and xt minus 1, which is gamma 1, covariance with a lag 1, minus 0.48 gamma 2 plus 0.064 gamma 3, and we also have covariance between xt and et is nothing but sigma squared, which is the variance. Similarly, when I now if I take the covariance with respect to xt minus 1, xt minus 1 and xt is gamma 1 is equal to 1.2 times xt minus 1 and xt minus 1 gamma 0 minus 0.48 xt minus 1 and xt minus 2 gamma 1 plus 0.064 xt minus 1 and xt minus 3 2 period lag, so gamma 2, and xt minus 1 and et nothing. Similarly, when I am doing for gamma 2 also, doing it with respect to xt minus 2, 1.2 gamma 1 minus 0.48 xt minus 2 and xt minus 2 will give me gamma 0, and again 0.064 xt minus 2 and xt minus 3 giving me gamma 1 plus 0. So these are the expressions, and probably even for gamma 3 I can do the same. 1.2 gamma 2 minus 0.48 gamma 1 plus 0.064 gamma naught. So these are the expressions that we are getting. So let me simplify the expressions, or let me write them down separately. Gamma 0 is coming out to 1.2 gamma 1 minus 0.48 gamma 2 plus 0.064 gamma 3 plus some sigma squared. Whereas gamma 1 is coming out to 1.2 gamma naught minus 0.48 gamma 1 plus 0.064 gamma 2. Now the gamma 2 is coming out as 1.2 gamma 1 minus 0.48 gamma 0 plus 0.064 gamma 1. And finally gamma 3 is coming out as 1.2 times gamma 2 minus 0.48 gamma 1 plus 0.064 gamma 0. So this is what is finally coming out. Right, so this is for the first one, whereas from the second one, when I am looking at, it is coming, it can be generalized like gamma k is coming out as 1.2 times gamma k minus 1 minus 0.48 times gamma k minus 2 plus 0.064 times gamma k minus 3. So this is the general form that is coming up. And so based on this, if I am simply solving, right, now that I have gamma 2, gamma 1s and all that stuff, I can very well do the simplification part. Right, now that I have gamma 2 equal to this in terms of this, so probably what I can do is gamma 2 is equal to 1.2 gamma 1 plus 0.064 gamma 1. So which is coming out to 1.264 gamma 1 minus 0.48 gamma 0. And even here, even out of this also I can establish the same. because if I'm taking the process to the other side, right, this gamma 1 and gamma 2, if I'm, so it becomes 1 point or gamma 2, even on this side, it comes out to me as gamma 1 plus 0.48 gamma 1, which comes out to 1.48 gamma 1 minus 1.2 gamma 0. This entire thing, I am dividing it by 0.064. So these two are coming out to be gamma 2's itself. So I can equate these two things. 1.264 gamma 1 minus 0.48 gamma 0 is equal to probably 1.48 by 0.064 gamma 1 minus 1.2 by 0.064 gamma 0. So it can very well be worked out that 1 point or we'll do it this way, 1.2 by 0.064 minus 0.48 gamma 0 is equal to 1.48 by 0.064 minus 1.264 gamma 1. So we are getting gamma 1 and gamma 2's. Gamma 1 in terms of gamma 0 is what we are getting. So let me do the simplification. So this works out to 1.2 by 0.064 minus 0.48. So this much 18.27 gamma 0 is equal to 1.48 by 0.064 minus 1.264. So it is 21.861 gamma 1. So gamma 1 is coming out to 18.27 by 21.867 gamma 0, which is 0.83 times gamma 0. That is what is coming out for gamma 1. Right, gamma 1 is getting simplified as almost 0.83 times gamma 0. Now the same logic I can go ahead in terms of gamma 2. I can simplify the gamma 2 also. Now that I have gamma 2 is 1.264 gamma 1 minus 0.48 gamma 0. So in terms of gamma 1, now I can very well substitute 0.83 times gamma 0. So this is going to give me this times 1.264 gamma 0 minus 0.48 times gamma 0. So it is coming out to almost 0.57 times gamma 0. Right, gamma 2 is coming out to 0.47 times gamma 0. So based on this, now that I know that this is gamma 1, this is gamma 0, I can very well divide now this gamma 1 by gamma 0 is what is autocorrelation for time lag 1, which will give me this is the row 1, and similarly row 2 also. Similarly, row 2 is gamma 2 divided by gamma 0, which is again giving me that this is the autocorrelation for time period lag 2. So I am able to compute the first two values, and these are my Euler equations. And describe the behavior of rho k and the partial autocorrelation function phi k. Now this is a time series with a lag of 3. So typically an AR3 process. So what we typically see is as rho is increasing, as k is increasing, as the time lag is increasing, this autocorrelation function should gradually go down to 0. And when it comes to the autocorrelation function, because it's a third order process, for any lag, partial autocorrelation function for 4, 5, 6, for all of them it will be 0 itself. Whereas the autocorrelation for an AR process, you will see that it gradually decays to 0. Whereas the partial autocorrelation function, after the lag, you will see that it will suddenly drop to 0. So that is the way out computing the autocorrelation for a time series using the Yule-Walker equation, and finally trying to find out the auto covariance and then the autocorrelation by solving those functions, right?